Well, thanks, Steve. Well, welcome everyone. I know it's a wonderful weather out there, sitting here, but this is a very nice, auditorium as well. So I hope you'll enjoy the next, hour and a half or 80 minutes or whatever we have. So again, it's a pleasure being here. Let me give you a little bit background before we get into the nuts and bolts of the presentation. Like Steve said, I'm the director for the Exploration Technology Directorate, but just a little bit of my background. So I grew up in India, as many of you can possibly guess. So I did my undergraduate in physics, because I was all enamored about quantum physics and how all these things work. But then, this is in the basically in the early 80s. So computers were becoming very popular, at least in India. Again, several generations behind the US, perhaps. So I decided that, well, I'm going to do an accelerated undergrad in computer science, like get a dual BS in computer science, because all the easy problems in physics are solved. I could have solved one of those, but all the hard problems are left. Whereas computer science is just coming up, there'd be a way to do things. So anyway, so I did an accelerated undergrad in computer science. I came over to the US. I went to RPI, Rensselaer, in the East Coast. I got my master's and PhD in computer science. I always wanted to work for NASA. So the only places I applied were at various NASA centers. I did get an offer at NASA Langley, which is in Virginia, and I was going to take that job. Because I had come to the East Coast from the US, from India, and I was very familiar with the East Coast culture and everything else. The West was kind of a wild West. Who knows what goes on in California? But two weeks ago, your speaker was Horst Simon, and Horst is a very, very long-time friend of mine, and he was at NASA at that time. And he said, Ripak, you should just come out here. Why wouldn't you come out and just give a talk, and we'll see if NASA Ames offers you a job or something. Anyway, so because of Horst, I came over here, and NASA Ames did offer me a position. And they did offer me twice the salary of what NASA Langley was providing. Again, these are tiny amounts, by the way, but it's still double. And I, foolishly at that time, accepted the California offer at twice the salary. I should have asked for an order of magnitude higher salary. But anyway, I did take it, and so I've been here at Ames since 1991. So I've been here for a long time. My phone number even at Ames hasn't changed over the last 29 years. So anyway, that's a quick background. So what I thought I'd do today, because we have a variety of attendees here, talk a little bit not only about HPC and those kinds of things, because I know that's what the course is focused on, but I think we need to understand a little bit of the context of why NASA is interested in HPC, because that is important. And I also know that not all of you might be interested in HPC, but there are careers at NASA that go beyond HPC. So here's just to put everything in context, exactly what NASA does. Now, many of us might only remember Apollo and landing on the moon. By the way, you know that the 50th anniversary is coming up next week, so it's a big deal. And for those of you who were not around at that time, this is probably all a myth or photoshopped. So maybe all you remember is the shuttle. And since the shuttle no longer flies, well, we don't really know whether NASA actually exists, or what NASA does is unclear. So this gives you a kind of an overview of what NASA does, but the important thing here is that there are large parts of NASA that go beyond space exploration. For example, aeronautics is a big part of NASA. It's the first day in NASA. It's the National Aeronautics and Space Administration. So aeronautics is a big part of what NASA does. We actually have very close collaborations between NASA Ames and, hey, how are you? We're just talking about NASA and you walk in. Okay, so we have nice collaborations between between NASA and Stanford on turbulence modeling and things like that. But aeronautics is a big part of what NASA does. But the portion that people hear about all the time is exploration. That's the HUMD mission directorate that is focused on all sorts of exploration, whether it be the International Space Station, whether it be the Swiss lunar space, whether it be this new Artemis thing, which we'll talk about briefly, and or things like robotic and human missions. And then, of course, there is science, because it's not just about the Earth or the solar system. It's also about planetary science. It's about astrophysics. NASA, being a space agency, has a very nice perspective on Earth than any of the Earth-based agencies like NOAA and others. So we can actually add value to even weather, climate, and all of that from a NASA perspective. And then finally, all of this is driven by by technology, and that runs the spectrum from whether those are going to be used for science missions or aeronautics or exploration. A lot of it is collaboration with academic partners, with commercial sector, maybe international partners as well. So that kind of gives you one spectrum of how NASA is organized. Another way of looking at it is how NASA is also a very large distributed agency. Most of us know the major centers, because that's where all the excitement is. People, of course, know Kennedy, because that's where all the launches happen. People know Houston, because we say, Houston, we have a problem. That's where the astronaut training is. But then, a lot of work does go on in the research centers. And so NASA has 3 research centers: Langley in Virginia, the one that I was talking about, and then we have Ames here, and then in Cleveland, we have Glenn Research Center. Now, the interesting thing, though, is that, and why aeronautics is so important, is that centers like Ames and Langley and Glenn and Armstrong, by the way, in the Mojave Desert, actually predates NASA. So NASA was formed in 1958, and these 4 centers were actually part of NSCA, which were then subsumed into NASA when NASA was formed. And so these 4 centers are also known as the aero centers in some sense, even though, because these are research centers, and a lot of things that we try to understand on how to fly better planes or drones also applies to fluid flow and rockets and combustion engines and all of that. So it kind of, these centers have morphed. So these centers have a large spectrum of activities that assist the NASA missions at all the other centers. So this is the official kind of the NASA chart as to what NASA is focused on. And as you can see, one interesting thing is all of these have the word explore in there. But again, you can see the wide spectrum of activities. And the reason for me showing this to you is that, as students or early in your careers, or you're trying to decide what you want to do, you can almost do anything and NASA is interested in it. You could be an IT person, you could be doing autonomy and robotics, you could be doing turbulence modeling, you could be doing engineering, you could be doing life sciences, you could be a cosmologist or an astrophysicist, you could be a lawyer and legal people, and we would need you. So it shows you that, whether it be in any of the STEM fields or things that go beyond that, we are always looking for people. And there's another reason we are also looking for people at Ames, by the way, is because we are losing a lot of people to these high-paying companies that are sitting right across us. So we also are very interested in workforce development and how they come and contribute to the NASA missions. But again, just to give you a sense of what all of these are, the first one, of course, is focused on aeronautics, exploring flight, the next generation of aircraft that are more fuel efficient, produce less noise, all of the advances that we need in next generation of flights that would help with mobility and the environment and all of that. Humans in space, of course, the International Space Station is a laboratory that has been in continuous operation, always populated, and it's also a huge demonstration of international partnership. We'll talk a little bit more about this Moon to Mars mission. Technology, again, enables all of that. We talked about Earth sciences, and then, of course, it's not just the Earth, but it's also the solar system and beyond. Just to give you a quick overview of what Ames is, because it's right down the road here. It's about 1,800 acres, formed in 1939. We are celebrating our 80th anniversary. We have about 1,200 civil servants. These are people who work for the federal government. We have a large number of contractors. We have tenants. We have this thing called the NASA Research Park, which is when the Navy moved out of the naval airspace here and Onizuka was closed, NASA was given control of the entire space. That includes the airfield as well. But that is where we have tried to incubate small companies. And many companies have come out of there. Bloom Energy is one of those, made in space. But there are many others that are based there, and the idea is that these would be ways of having closer collaboration between what NASA core is interested in, which is inside a smaller 400-acre space, and the larger. And again, there's also academic partnerships, by the way. Carnegie Mellon has their West Coast outpost over here. We have Singularity. We had the chancellor of, just to put some pressure on management here at Stanford, we had the chancellor of UC Berkeley visit us today, because she is very interested in having a UC Berkeley outpost at Ames. And you may have heard in the news that USGS just moved out of their Menlo Park offices that they have held on for decades, and they have moved into the NASA campus, because this is becoming more of a federal city as well as with close connections to academia. So we talked about what NASA at the larger level does. These are the kinds of things that we specifically do at Ames. Air traffic management, again, you can talk about aeronautics, but air traffic management is, on any particular day, there are thousands of flights that are in flight. And if you now throw in all these drones and UAVs, then you can think about this is a very complex problem that will require a lot of effort. And then if you throw in uncertainties such as weather and rerouting and all of that, that's a big area of research, and Ames is the kind of the lead center that does ATM. Entry systems, there's always a joke within NASA, or at least a joke that we have kind of kept going, is that if you want to go to space, then you should go to Kennedy, because you can't go to space without Kennedy. If you have a problem, you definitely need Houston at JSC, because no one else can help you. But if you want to come back, there's no way to come back unless you come through Ames, because we are doing the entry systems technology. This is developing materials and heat shield materials that will protect you, astronauts or payloads that re-enter Earth, or any atmosphere, any other planets or bodies that have an atmosphere that you have to enter. So we run what is known as the arc jets. So one way of looking at it is it's like a big wind tunnel, but it's a wind tunnel combined with a microwave oven in some sense. So we are testing materials that could be either ablative or reusable materials, and try to test them by exposing them to really high radiative heating and trying to see how they behave. And these are the things that would go on vehicles that would enter any atmosphere. Advanced computing and IT systems, that's what we're going to talk about a little bit more today. And of course, intelligent adaptive systems. These are all kind of bleed into one another. I think the whole definition of HPC is broader than when we first started doing HPC, which was all about supercomputing. But now it bleeds into data sciences, into data intensive computing. But even things like machine learning and deep learning really cannot be done unless you have a supercomputer. The bottom row, NASA's missions are always big, and there are billions of dollars. But one of the things that we had done several years ago, about 15 or so years ago, that we pioneered at Ames and has become very popular, is now can you get 80 or 70% of the science done for at maybe 10% of the cost? And this is the idea of having small sats or nanosats. And this has become so popular that I'm sure people at Stanford and even at high schools, you can put these small sats into space and you can get a lot of science done, maybe not at that same level. And because these things are extremely cheap, you don't care if they all survive. You can also use them as constellations, in that where several satellites might be working together to accomplish a certain mission. Even though one or two of them might fail, you still get most of your mission done. Aerosciences, again, it's not just, we run some of the biggest wind tunnels. The largest wind tunnel in the world is at Ames. The test section is 80 feet by 120 feet, so you can put in almost a fully aircraft in there. But we have also tested parachutes as well as 18-wheelers and how they would behave if you had crosswinds on highways. But it's also about this computational fluid dynamics that go into it, whether you're doing Navier-Stokes, Euler equations, or you're trying to do more LES and DNS and turbulence modeling and all of that. And then finally, one of the things that we had pioneered at Ames is looking at life sciences. It's almost like how could life be created, for example. And so we had formed this NASA Astrobiology Institute about 20 years ago. It's a virtual institute that's at Ames, centered at Ames, and try to understand, it's not only about finding life, if life exists out there, but also about how we can extend life out there. Because again, if you think about it, it's a little certain nuance about trying to find life somewhere else deep in the universe, or can we propagate life out there deep in the universe. And then finally, space and earth sciences. One of the interesting things that we have is we have a 747. We got a hole in the back. We put an infrared telescope in there, and that can be used for a lot of observational data gathering. Right now, this project is called SOFIA. It's a collaboration with DLR, and currently it's in New Zealand on a mission over there. So given all of this, well, then you can probably imagine why we need advanced computing. I'm not going to read all of these things, but the idea is that, how do you actually solve problems? One, of course, is the theoretical way of solving problems. You have equations, you use slide rules, you write down equations, you solve them. So that's one way of doing it. The other way of doing it, of course, and none of these, all of these are complementary efforts. Another way of doing it is you actually do flight tests, right? You can build things, you can blow them up, you can see what happens, you can fly them, you can crash them, you can put them in wind tunnels, you can do a lot of things. And then, of course, the third aspect of this is you can do computer simulations. And all of these are kind of complementary to one another. Now, obviously, as the power of computers have become more and more, significantly improved, you can see that you can do more with computers. However, remember, and many of you who are computer science majors, you can write any program and you can generate garbage at infinite speed. So you have to also understand that the results that you're going to get out of computer simulations will depend on how good your models are. It is not about just getting big computers and throwing more grid points at it. You have to get the underlying physics and chemistry involved. The simple example I give people is that if I'm doing a global ocean model, okay, I can do it at 1/4 of a degree, I can do it at 1/12 of a degree, I can do it at 1/48 of a degree. The more and more powerful computers I have, I can throw more and more grid points. But I cannot just continue to solve the same problem, because at some point then I have to start considering the whales and the dolphins in there. And if I just assume that it's a homogeneous fluid, then all my answers are basically wrong. I'm just getting them faster by having a faster computer. But so I think, and then of course there are two other additional advantages of doing computing. One is you can do predictive stuff. You can predict things what can be done, because as long as you have a model that you can verify, then you can use that model to predict things that could happen in the future if you did certain things. And then the other thing that is interesting for computing as well is that NASA does a lot of observational data sets. So we have large amounts of data, and so you can use your computers to mine that data to get more intelligence out of it. But when we talk about computing, I think the initial tendency would be that we are always talking about supercomputing per se, because that's the traditional way of thinking of computing. But there are many other things that I consider part of computing. For example, in the field of computing, there are only two known other ways of doing computing at a broad level. One is quantum computing, that where you're going down to the small atomistic levels and at low temperatures to see if you can use some of the quantum mechanical effects to solve certain problems. And then, of course, going the other way, which is kind of brain-inspired computing, which is called neuromorphic, where you're using how the brain works and how neurons and synapses occur in order to solve certain problems. But other than that, there are also other applications. And again, not all of these fall in the same class. For example, machine learning could be considered an application of supercomputing, and cloud computing could be thought about more as a business delivery model as opposed to computing itself, even though it's called cloud computing. But there's really no difference between a cloud computing and a supercomputing, except that the supercomputing is sitting somewhere else and you're accessing it remotely. So there are all kind of different things. And then, of course, we have to also consider when we have large amounts of data and when a community comes together to solve certain problems, what kind of collaborative environments do you want or need in order to solve a certain problem. So at a very broad level, if you look at what NASA's requirements are, they come in kind of three classes. One is that you're trying to solve what I would consider a high throughput or a capacity problem. They're not completely independent calculations, but let's say you're trying to design a rocket. And you have various parameters and you want to model all of them, and you cannot finalize the design of the rocket unless you have looked at this whole parameter space. And the parameter space could be n-dimensional, so you may have to run many, many runs. Now, each of these runs probably do not require more than 1,000 or 2,000 cores. But you cannot finalize your design unless you have run this entire or generated this entire database, let's say, or this parameter space before you can do that. So I consider that kind of high throughput computing or capacity computing, where each run is probably only 1,000 or 2,000 cores, but you need a large number of them in order to make a final decision, even though each of these runs could be done in parallel. So they might be running the same code or maybe running slightly different codes, but with slightly different input parameters to solve a certain problem. The second class of problems, and obviously within NASA we have that if you're going to build big rockets and space vehicles. But then you have the other class of problems where we are trying to solve a single problem with the highest fidelity possible. So if I'm trying to do a global ocean modeling and I want to throw in the atmosphere and the land and the sea ice and clouds and all of that, I don't have to run it 10,000 times. I just want to run the largest one I can run with the highest fidelity, with the most physics and chemistry and all of that in there, and I want to run it. So in that case, I want the largest possible computer I can fit this in. Or suppose I'm trying to solve an aero problem, and I'm trying to solve a helicopter problem, and I want to capture the rotor wake. So I don't need to do 10 different calculations of the rotor wake. I want to be able to refine the rotor wake as much as possible, so be able to put in as many grid points I can in the rotor core, in the vortex, and then I want to kind of see that over 5, 6, 10, 20 revolutions or rotations, so I can get the effect of that rotor wake on the fuselage and the wings and the blade vortex interaction or high speed noise on all of that. So you have that, and then of course NASA being a mission agency, a large part of what we do in supercomputing is also supporting missions. So there is also a need. Now this was very important during the shuttle days when the shuttle was actually flying, because we would have to do real-time or near real-time analysis of any falls that may have happened, in the sense some tiles may have fallen or not during liftoff, and was the shuttle still safe to come back. Now, those things are not critical at this time, but you can think that as we get more and more into human missions, they could become critical again. So there is also a need to be able to provide availability and guaranteed services in some sense. So again, this is just more of what the systems that we have. Again, we don't have to spend too much time on it, except that several years ago, NASA had decided that computing was an important part of what NASA does, and that there was really no reason to have computing spread across all over the agency. As you saw, we are a fairly distributed agency. We obviously have expertise in different centers in different fields, but there was no reason for computing to be distributed, because you could actually use, you could do it much more optimally by having it in one place, so you can have the IT security and the patching and all of that done. And it was decided that Ames, because we have a long history in computing, to have these systems. And so we have, two systems right now which are fairly big. They're in the top, 30, 40 in the world. Together they have about 15 or so petaflops. But then we have also done other things in the sense that we were pioneers in building this concept called a hyperwall. Now you see that everywhere. But one of our ideas also was to use a large number of fairly smaller screens. So here we have a panel of 128 screens, because one of the things that we were also interested in, rather than looking at large images, was also looking at sets of related images, so that scientists and engineers could look at relationships between these images to get more additional information out of this than that would normally come. Now, one of the biggest problems of computing is that, the bigger and bigger these computers get, the bigger and bigger power stations have to be. So we have an exaflop machine sitting next to a nuclear power plant and probably a beer factory, because all the water is needed. So I don't know. But one of the things that we have tried to do is try to use the wonderful weather in the Bay Area to be able to do this modular thing. So this is one of the things that we have done. We already have the two versions of it. The machine up there, which is Electra, is already 8 petaflops sitting in a container. Remember, that big machine that is sitting in a brick and mortar building is only 7 petaflops. Here it's taking up 1/10 of a space. It only uses less than 1% of the water, and it has this thing called the PUE, which is the power utilization effectiveness. That is a ratio between the power that is needed divided by the power that is actually used to run the computer. So ideally it will be 1, because that means if you get 1 megawatt of power, the 1 megawatt is going to the computer. But usually in most places it's something like 1.3 or 1.25. That means about 25% of the water is being wasted. So the big machine called Pleiades that we have in our building, that has a PUE of something about 1.2 or something. Whereas here is Electra sitting out at 1.03. So that means only 3% overhead is needed to run. And so because of that, we are in the process of building this big 1-acre pad, which will have 30 megawatts of power. And the idea is that we'll put modules in here similar to those ones. We obviously don't have all the money to populate all this, because if this was entirely populated, this would be several hundred petaflops. But that's not what we want to do anyway. The idea is that as computer technology changes and matures, we can be flexible, and then we can put different modules having different things. Some may have GPUs, some may have ARM processors, some may have more of the traditional things, some may have more attached memory, some may have a faster interconnect. But you can do all those different things and be kind of agile in the sense as to what kind of computing is needed, what for NASA needs. So, but that is in the process of getting done, and so we have a grand opening celebration of that next month, and so we should have the first 2 modules in there. And then, if you have a lot of money, you can go buy computers. That's not a hard thing. Everybody, companies have big computers. Google has big computers. Other companies have big computers. So buying more computers is a very simple process. But the question is, how do you use the computers to actually do something useful? So again, this is a slightly complicated chart, but if you just focus on the overall idea behind this, is if you start at the top, you have these various NASA mission challenges, whether they are, like I said, aeronautics, earth sciences, exploration, whatever that might be. And the idea is that there are simulation codes that we are running, and then we need to do the performance optimization. We need to have experts in computational science and computer science and programming languages and understanding the architecture of the system to be able to map these efficiently on these systems, and then also think about how these would be ported into future systems. So that's where the value comes in. And then, of course, all the various analysis parts of it, and then finally the visualization aspect of it. So it's this combination of what we consider as a spiral support system, where you get the user requirements, you do the optimization. We are not writing the codes or anything. Those codes already exist, let's say, or the domain experts have written them. We are implementing them properly on the systems that we have, and then we provide the feedback through the data analysis and the visualization that then allows the next wave or the next set of innovations to be implemented into the domain, and so you can continue to do this cycle. So So that kind of gives you a little, high-level thing of what we're doing. But one thing I thought would be interesting to talk about today is because everyone is talking about it. And so it might be interesting for you guys to also hear a little bit about it. So one of the things that happened recently, because NASA had been to the moon, we have had 12 men walk on the moon, and we are celebrating the 50th anniversary next week. And so we had focused on kind of two things. One is we are going to go to Mars, and that we will transition the International Space Station and low Earth orbit things to commercial sectors, because that they can do it more efficiently than we can. However, with Space Policy Directive 1, the administration made an announcement that NASA will land the first American woman and the next American man at the south pole of the moon by 2024. And that would be followed by a sustained presence on the moon and beyond by 2028. And it actually says, and we can all read what that means, use all means necessary. We are not going to discuss that. But the idea is that there is a huge pressure within NASA that we are going to have a woman and a man on the moon by 2024. Now, it may seem a little surprising, but it's actually not that surprising, because we were prepared to do this by 2028. The only thing that has changed is the acceleration of this whole activity to get this done in 2024. So now, why do we want to go to the moon? Because that's a question that people might have. We've been there, done that. We should go to other destinations. But, and you can read all of these things. But I think one of the most important things is that it allows us to have a sustained presence on the moon. Because even though we have had humans on the moon, those were all short duration trips. The question is, can we sustainably live off the land and stay on the moon for long duration of time? So this mission, and you can all look it up, but just giving you a quick overview of this, it's called Artemis. And the reason it's called Artemis is because we are going to have the first woman on the moon. It's the twin sister of Apollo and the goddess of the moon in Greek mythology. And so two new things are supposed to happen. One is we will have the first woman on the moon, and two, we are going to be up in a place in the moon that we have never been before, which is the South Pole. But that ties into this overall broad strategy, even though that seems to be a near-term activity, and large portions of NASA are focused on it. It fills the larger spectrum of what we always wanted to do. Is we have the Earth orbit, which is things that we're doing with the International Space Station. We have the lunar orbit, cislunar and all that. We have the lunar surface, trying to understand in situ resource utilization, living off the regolith and all of that. And that lets us get to Mars and beyond. Many of you probably have seen some version of this slide, but now these names have changed. For example, Artemis 1, which is going to be the first human spacecraft to the moon, was called EM1. It was called Exploration Mission 1. So it was called EM1. Now it's Artemis 1. EM2 was going to be the first flyby of the moon, and that's now called Artemis 2. So it's just a change of names. And then the new thing, of course, is Artemis 3, which is having a crewed mission to the lunar surface. So that's kind of the spectrum. Artemis 1 is supposed to happen in 2020, and Artemis 3 is supposed to be in 2024. And then, of course, all of this has to be supported by a whole bunch of other things, which is, we have to have cargo there, and, there's also it's not just a vacation or a tourist visit. We want to do science, so we have to take payloads there. You have to take payloads there, and then how do you actually do all of that with commercial partners? So we also have a program called Commercial Lunar Payload Services, called CLIPS, and that is the one that is going to be already granted to 3 companies, but that will allow other payloads, science instruments, and things like that to be delivered there. So again, kind of reviewing that again, on the top line, if you see, we have the crew. So that's Artemis 1, which is the first flight test of this thing called SLS and Orion. I'll talk a little bit about that. And then Artemis 2 is just going to be a lunar flyby, and then Artemis 3 is landing on the moon. Then we are going to have the cargo thing, which is we have to get the power and propulsion element at this point in space. Because remember, if you think of, and again, I don't know, maybe you guys don't know this, but when we did the polar missions, we had the command module, right? So while Neil Armstrong and Buzz Aldrin were on the moon, Collins is sitting in this little thing and he's flying around the moon, so that when these guys are done, they have to get back to the moon, get back to the capsule and get back to Earth. So how are we going to do it now? We can't just land them there. We have to somehow bring them back. So we are going to have this thing called the gateway. And the gateway is, if you think of it in some broad context, is similar to the International Space Station. So it is going to revolve around the moon continuously, unlike the command module for Apollo. So it's always going to be there. And from that, we'll have this human landing system. So there'll be a transfer vehicle that will transfer the lander from the gateway to some lower lunar orbit, because the gateway cannot be too close to the moon. So the gateway is spinning around the moon some far place. There's going to be this transfer vehicle that will take the lander and will transfer it to a lower lunar orbit. And then there'll be a descent vehicle that then descends to the lunar surface. And then after the lunar surface is done and all that is done, then the ascent vehicle gets us back to the gateway. And that's where our SLS and MPCV are waiting to get us back to the Earth. Okay? So it's a fairly complicated sequence of things. So this is going to be the big rocket. This is called SLS. And on top of it is going to be Orion, which is going to be the crew module. And as you can see, this is going to be the largest rocket that has ever been built. Last week, we tested out what is called the launch abort system. So if you think of it, so you have this big, massive rocket, which is, I think, compared to about 14 or 16 Boeing 747s at the same time thrust. On top of it is the Orion capsule. That is where the crew is. But on top of the Orion capsule is a launch abort system, which is another tiny rocket that is sitting on top at the pointy end, so that in case something were to go wrong, the launch abort system can pull the crew off this stack. Because you're sitting on this big firecracker, right? And if this firecracker has some problem, I have all those 3 or 4 guys over there and gals, we'll have to get them out. So we just tested that launch abort system, which is going to take the capsule off the top of the stack and take them somewhere else before this thing explodes on the launch pad. And then this is the gateway. So this is how this is all going to work. So this is the thing that is going to fly around the moon. And this is where MPCV will come, and it'll attach to it. And then you'll have the lunar landing system, the ascent, the descent, and the transfer things getting off on that. And a lot of this is still not completely fleshed out, and a lot of these things will be trimmed down to a version that we can get done by 2024. For example, instead of this being kind of a mansion that we had envisioned, this is probably going to be a little outhouse or a barn for 2024. But then later we can put in carpeting and all of that. But right now that's how it's going to be. Okay, so there's many more things on that. I didn't want to just say that it seems like a big mission that we're doing to as a stunt or something. There's a lot of science that is supposed to be done by 2024, and there is a lot of technologies that are needed. But this is an interesting concept, interesting slide, because it also shows that there are many other things that will be needed to make this work. So for example, we need solar electric propulsion to get there. We need precision landing. We just cannot land willy-nilly. We have to land within a certain point of where we need to be. How do we do that? There's high-performance spaceborne computing part of it. There is also how do we live off the lunar surface? How do we get into extreme places? The lunar lander is not going to be able to get into all kinds of weird, tiny places. How would we get there? How would we generate power on the lunar surface itself? So there is all of these other things that have to happen also in order, if you want to actually live off moon or any other place like that. I'm going to skip this slide, but this just shows that even though the focus is on the moon, there is a longer-term sustainability goal of how we can live there and then go on to Mars. And then, of course, there's a science part of it. So again, now bringing it back to HPC. So how are we kind of supporting all of these things? So what I'm going to do is I'm going to show you a bunch of animations over the next few slides to show you the kind of computer simulations that we are able to do. As you can see, this is kind of the launch pad. So this is SLS, and we are looking at the first few seconds of it. This is after the engines have been fired, but the rocket has not actually moved more than a couple of feet at this point. Okay, so it has just taken off the launch pad, but it hasn't actually cleared the tower yet almost. So various things happen. One, of course, is the huge plume that comes in. We are trying to solve the hard problem, because what we are actually going to do in reality is we are going to throw gallons of water on this also. But we are looking at it without the water in some sense to see the worst case situation. We have to understand how this flame comes out. We have to see how the flame range behaves. Just to put everything in context, these little green men are not going to be standing there. This is just to show you the size and the dimension of them. They're not standing there when this is happening. But we have to also understand how the flame range behaves. What is the ignition overpressure of this vehicle? Because there's going to be a reflected reflection going to come off and hit the rocket itself. That could affect the stability, because the rocket is still just hasn't taken off yet. So you don't want the rocket to tilt or something happens. And then, of course, there is also acoustics that you have to worry about, because you may have payloads in there that might get damaged because of all of that. So just to give you some ideas, rather than getting into the more details of how this is all done, you can see there's a lot of work that is needed in terms of gridding, in terms of developing these solvers, understanding the visualization aspects of it, trying to capture every little nut and bolt, because the more accurately you can get the design, the more accurately your results are going to be. You can say, okay, there's a little protuberance there, I'm just going to ignore it because it's just too complicated. Well, then your flow is not exactly what it is going to be. And so all of these little things are important. So then after that, at about Mach 4, at about 100,000 feet, the solid rocket boosters are no longer needed. They are depleted, so they have to be separated out from the main stage. But one of the biggest worries is that you don't want them to separate and then come and recontact. And so the number at the bottom left shows you the distance in feet from the tip of those solid rocket boosters from the core stage. Because as they fall out, you don't want them to come and somehow touch the main core stage. Again, these are particles that are colored by velocity, I believe. But you can also see the launch abort system sitting on top of the MPCV. So you can see right there the launch abort system, the Orion crew exploration vehicle, and then the core stage. And this shows that the two SRBs are falling off. Of course, then there is also the launch abort system, like we talked about. This is the one that is supposed to take you off the stack and then deploy parachutes. The one that we did last week, we did not have the parachutes. And so we actually told all of our employees who were watching, because what happened is that the abort system picked the module up and then crash landed it somewhere. And if you didn't know it, you would think, oh my God, this was an utter failure, because all these people inside are now crushed to death. But that was the purpose of the thing. Only thing we didn't do is we didn't use the parachutes. But in the real case, there will be a parachute so that it doesn't happen like that. There are many more other aspects of this as well. I wanted to get to some other parts of the talk, but this also shows that it's not about just the launch vehicle itself. During the flight, you want to look at acoustics, you want to look at loads, you don't want to lose control of your vehicle. So there's a whole bunch of other things you can do. We have also done massive simulations on parachutes, because some of the parachutes that you will require in atmospheres that are less dense, they need to be large. And you cannot, so we have done parachute testings in our wind tunnels. Like I said, they're 40 by 120 feet. So you can put large parachutes in there, but they cannot be as large as the ones that we need at supersonic speeds, because that's not a supersonic wind tunnel. And then if you have a supersonic wind tunnel, because then they're tiny, but then you can't put the big parachute that you need there. So these are kind of parachutes that you need, that we used for Curiosity, but the only way to kind of test these parachutes out are through computer simulations. And so it's important that your codes and simulations and your assumptions are all there to be able to make predictions that make sense. Now, I wanted to also spend a minute or two maybe on some of the aircraft work that we have done, especially on the noise characterization. Some of the things that we have done is looking at jet noise simulation. Now we are talking more about external flow, but also noise that is coming from the engines. We had looked at some of the landing gear noise because that's another huge source of noise, and that affects property values because I like to fly, but I don't want the planes flying over my house. So again, lots of different types of calculations. Even though we put this in this broad class of CFD, a lot of special calculations have to be done looking at engineering design and viability of these products or vehicles, but also making them efficient. We had looked at internal flow. Now we are looking at fan noise. And then finally, if you're now looking at urban air mobility, tying this back to ATM, how are we going to be able to do these things if there are not only these aircraft, United and Southwest flying, but everyone is flying their own little drone? And so we had started off by looking at some of the helicopter rotor acoustics and aerodynamics. These were some of the largest calculations. These are a few years old, but these are some of the largest calculations we had done, where we had looked at the rotor wakes coming off the tips, these tip vortices, and how, and as probably you can guess, unlike an aircraft where vortices occur, but those do not affect your plane itself. It just goes downstream, and maybe it's the next aircraft that is coming, and so they have to be 90 seconds behind you or 60 seconds behind you so that they don't get affected. But in a helicopter, you are affecting your own blade because your next blade is coming and hitting that. And there's been a lot of engineering work, is that can these blades be morphed as they go around? Because some of the blades in one direction is actually helping with the lift, but the others are actually causing harm. And then, of course, how does it affect your fuselage if you're looking at the downflow of these vortex wakes? And then we had done also some recent calculations that looking at drone rotors where you have octocopters. One of the things that maybe you have heard recently with Johns Hopkins Applied Physics Lab, we at NASA Ames are going to fly this mission called Dragonfly. So this is a mission that is going to go to Titan. This is the moon of Saturn, and the moon of Saturn has some atmosphere, and so we are going to fly this octocopter there. And so instead of just having a rover that can just go from one place to another, this octocopter is going to land on Titan and then do some work there and then go to another methane lake, so it can fly there. So it will have more mobility rather than a rover. So this is a very exciting mission that includes helicopters as part of that and autonomy. The only problem is that this mission does not fly until 2026 and does not get to Titan until 2034. So some of us will be probably in our, I don't know, rocking chairs and wondering what the hell this is. But for many of you, 2034 is not that far away, and in 2034 we are supposed to have this mission to Titan. And the idea is that Titan still has many of the prebiotic conditions that existed on Earth. Because we all talk about carbon, hydrogen, and water and all that, but there is still a mystery how life suddenly could come out of that. So you have all the ingredients, you can put some hydrogen, carbon, and everything in there. That doesn't mean suddenly a worm is wiggling out of there, right? So how did this all occur? And so this experiment at Titan, this mission to Titan, is supposed to let us know that. And then we have similarly, there's a lot of work in heliophysics. I'm going to skip over that because I want to get to the last portion of this. And then we have done significant work also on global ocean modeling. One of the things, again, just I wanted to touch on this, is that in the past, because we did not have very powerful supercomputers, if you wanted to do regional modeling, what we would do is we would do a global modeling and then kind of just downscale it to a small region and then just do a finer calculation on the smaller region. Suppose if we want to see what is happening at the tip of South America, for example. But the problem of doing that is then you're inserting errors at your boundary conditions. You're just kind of either extrapolating your results back in there, and then your boundary conditions, and then you're solving that. But now with large supercomputers that we have, for example, now you can do a global ocean modeling, the one that is on the left, which is at a 1/48th of a degree resolution. So you can do the entire ocean, and then you can zoom in on areas that you care about, whether it's the Gulf of Mexico, whether it's the Gulf Stream, whether it's in some parts of Japan or Indian Ocean. You can do all of that. I'm going to skip the next couple of slides because I wanted to talk a little bit about another area of high performance computing, which I think is very important, which is these collaborative environments. In certain fields, in aeronautics, in earth sciences, a lot of the work is done by the community. It's not like building a rocket. Maybe there's only a few people doing it or a few companies doing it. But in earth sciences, you have observational data. You can do a lot of things. And one of the problems that we have had is that these observational data sets are freely available to anyone. People download them. People write some code. People write a paper. They publish it. But then that whole thing gets lost. That whole workflow gets lost. How did a professor sitting in North Dakota downloaded a MODIS image, wrote a code, wrote a paper, made some predictions? Can someone build on it? That was unclear. So we had done this thing called a NASA Earth Exchange, and this is a kind of a model that could be used for many other things, and we have done this now also for heliophysics, which is the idea is that you have almost like a social network. You have virtual collaboration. You provide some tools there. Some modeling codes are in there. You provide all of the data. You provide some computing capability. If those people have the certain access rights, they can access the NASA computers. If they don't have that, we have an OpenNEX version of it, which is a collaboration with Amazon EC2. So you can actually run it on the Amazon cloud. And then you can post your papers. You can also put your workflow in there. And so now some of it, of course, is everyone has to want to do this. If you don't want to do it, then of course it doesn't help. But by and large, earth science community is collaborative. So what we have seen is that by providing a platform like this, it is easy for the next person to come in and then build on what someone has already done in terms of either reusing the workflow or reusing the code or the results. And significant science results have come out of that. So let me try to get to the last, maybe I don't know how much more time I have, maybe 5-10 minutes. But I wanted to finish with a couple of other things because I think this is also very interesting in the sense that, traditional computing has been around for a long time, and there is a huge effort within the federal government and everywhere around the world to get to exaflops and all of that, but there are certain problems that will never be solved on an exaflop computer or even a 100 exaflop computer. Because, and a simple way of thinking about it is that things that are polynomially complex, things that grow as n squared or n cubed, grow very fast. Now, we in computer science use all kinds of technologies to get them out to log n over log n log n, all those complexities. But even things like n squared, n cubed grow very fast. But if you think about it, 2 to the n grows really fast. So things that are exponentially complex, it will never be able to solve. So that means if I just, if something of complexity n squared, if n goes from n to n plus 1, it's an effect, but it's a relatively small effect. When n goes from n to n plus 1, n squared becomes n plus 1 squared. Okay, so that's not a big deal. That's n squared plus 2n plus 1. I throw away the 1, I throw away the 2n, so it's n squared. Okay, so it's order n squared. But when I go from, if anything is of order 2 to the n, if n grows by 1, my complexity is doubled. So that's a huge growth of complexities. And many problems are of that complexity, right? If you think about things that are optimization in nature, like a traveling salesman problem, planning, scheduling, any of those problems that have that kind of complexity, those problems will never be solved. And it's not that we don't solve those problems currently on traditional computers. We use heuristics. For example, we solve the traveling salesman problem. We are solving air traffic management. UPS definitely solving how to move packages around. How do they do that? So it's a simple thing. Many of you are computer science majors. You know how to do this. But for those that may not know this, the simple thing is if you are given a traveling salesman problem, which is you have a bunch of n cities and you want to, and some of the cities are connected by some number of roads. Not all cities are connected, and you want to find the shortest path for this person to travel all the cities. And it's a very hard problem to solve if n is larger than a certain number. And so the first thing you would do, which is a very smart thing to do, normally speaking, is you just look at the road that is the longest road, and you just delete that road. You just say, I'm just going to ignore this road between any two cities. You just look at all the roads that are there, sort them by distance, and the longest road you throw away. And you say, I don't know what the final answer is, but I bet the final answer never traverses that road. So I'm going to just throw it away, because then my answer to the problem is still going to be the same, because that road doesn't exist. I'm not going to use it. And so if you keep doing that, and if you keep throwing away the longest and longest roads, then your problem will become tractable. And then you will solve the problem on a traditional computer. What you have forgotten, though, it is entirely possible that the optimal solution actually used one of the longest roads. You don't know that. But there is no way to solve it, because then it's an NP-hard problem. So quantum mechanics, and again, this is a very high-level view of this thing, is quantum mechanics have all these properties that says that at very small scales and at very low temperatures, you have these three properties, which are superposition. That means you can be in multiple states at the same time. You can do this thing called tunneling. Because of the wave-particle duality, you can go through barriers, not walls, but certain barriers. Barriers have to be of a certain kind. And then, of course, it has this concept called entanglement, where two atoms are entangled. That means one knows the state of another, independent of how far apart they are, and independent of the speed of light. Because classical physics says that any two particles would know the state of another as long as it can get the message around. So if I say, hey, I was red, I just became green, I can tell this guy that I just became green. All I have to do is send a message, and that message will take as long as the speed of light. But that's not entanglement. Entanglement means if I change from red to green, this guy immediately knows that I'm green, immediately, independent of how far apart I am. Superposition, like I said, like I talked about, it's being in multiple states. So for example, if you have a register of 3 bits, you could be in one of any 8 states. If you have a quantum bit, then you could be in any of those 8 states but superposed. So that means you could be in all of those states at the same time. The only problem, of course, is in quantum mechanics is anytime you try to read it, it has to come down to a classical state, because you are now reading in a classical state. So that means those 3 qubits would still give you one of the 8 states. And then because of this whole uncertainty within quantum, each time it gives you a different answer. So on the face of it, this is a complete disaster, right? Because it has all these promises, and you can solve anything, but when you try to get an answer out of it, it just gives you an answer randomly. Okay, but there are ways around it, and there are many ways to do this. So the basic fundamental principle of a quantum computer, again, we are talking about computing. There are many other ways of using quantum mechanics. It could be for quantum sensors. It could be for quantum key distribution. It could be for quantum encryption. It could be for quantum networking, all of that. But for computing, basically, there are many ways of doing this. The ideal thing that you need is a qubit. That means you need something that can be in multiple states at the same time. And there are many ways of doing it. There are superconducting qubits. For example, one of the things that we have at our facility at Ames is we have these superconducting qubits. So they took a metal called niobium, and they made a little loop out of niobium. And then if you cool it down to 20 millikelvin, then it becomes superconducting. And when niobium becomes superconducting, electrons are flowing both clockwise and anticlockwise. And then if you have a circle and electrons are flowing clockwise and anticlockwise, then you have a magnetic field both up and down. So that's your qubit. So if you have a qubit, I've cooled it enough, electrons are flowing both clockwise and anticlockwise, I have a qubit because I have both an up and a down magnetic field. The only problem is if I want to read what that qubit is, I have to put in a transverse field, and then right away the electrons flow in one or the other direction. And then they do it randomly. So then it could be up or down. So building a qubit is not hard. I'm sure there are qubits, and in fact, we had a big celebration on Monday with Professor Yoshi, because Stanford is getting into a big collaboration with NTT Research. NTT is this Japanese AT&T, and so they're going to form a NASA NTT Research Park here in collaboration with Professor Yashimoto here, who is a faculty at Stanford, and they are going to look at certain qubits which are going to be specifically devoted to solving optimization problems. So why is NASA interested in? We have a large number of applications that could benefit from quantum computing. Air traffic management is one. So any planning, scheduling is an optimization problem. So there you need quantum. Sensor placement. Even if you look at data fusion. So for example, if I have images of the Gulf of Mexico, any one of those images could give me a lot of information. If I have hundreds of images of the Gulf of Mexico at different spectrums, at different times of the day, different times of the year, I could probably merge them and get certain additional information that is not available from one single information, like data fusion or image fusion. My challenge is that I don't know what subset of those 100 images I should merge, because I don't know what I'm looking for. And many people say quantum computing is like looking for a needle in a haystack. It's actually not true, because looking for a needle in a haystack is a very simple problem. Because I give you a haystack, I told you to find a needle. You know what a needle looks like. I can put 10,000 people on the haystack, so every person has a needle in their left hand, picks up a hay, compares it, sees, hey, is it a needle? No, it's not a needle, throws it away. That's the next thing. This is a simple problem. Quantum computing is not that. Quantum computing is, I've given you a haystack, and I've told you, I think there is something there. That's the problem. Now I don't know whether it's a needle. It could be a diamond. It could be a penny. It could be a battery. It could be the hay itself. I have no idea. And throwing 10,000 people at it is actually going to make matters worse, because everybody will come running to me and say, hey, Rupak, I found a penny. No, I was not looking for the penny. And someone comes and says, I found a battery. I was not looking for that either. I don't know what I'm looking for. So it's actually a very difficult problem, and that is what we are trying to solve. Now, the problem is whether anything can be solved or not is still an open problem. The idea of doing the way we do it is this thing called quantum annealing, which is basically, you are trying to get to, so if you think of that landscape, that energy profile, you're basically trying to find an optimal answer. So in some sense, basically you're trying to find the lowest energy state. So you want to get to the lowest energy state. So in classical methods, what we do is we use Monte Carlo. You can get stuck in a local minima. Then you have to use some sort of simulated annealing to bump you out of your local minima to find the global minima. But in quantum computing, because of tunneling, you don't have to go up above the barrier. You can just tunnel through the barrier to find the global minimum. Obviously, barriers have to be a certain kind, but the idea is that you can find the global minimum using quantum systems. So this is the system that we have at Ames. This is the largest quantum annealing machine. This is not a universal quantum computer. You will hear more about quantum qubits and neurons and all that, I think, in the next week from a very accomplished speaker. But we are looking at, but this is a machine that is only focused on annealing. It only solves one problem. It solves that optimization problem. And all it does, it tries to get you the lowest energy state. The problem, of course, is, like I said, every answer that you get is a random answer. So you don't know if that's the right answer. So the way we do it is we run the same simulation millions of times. Each run only takes about 40 microseconds, independent of what you solve. And so we run the same problem over and over again. And the answer that appears the most, if you're trying to get to an optimization answer, we assume that that's the best answer. That may not be the right answer, though. Or if you're trying to find the minimum answer, we run it a million times, and whatever is the lowest answer is the answer. So suppose we know the problem's right answer is 3. That's the lowest number it can ever get. We run this thing millions of times. We get 6s, we get hundreds of 6s, we get a few 5s, and we got 1 4. And we ran it a million times. We say, okay, then the answer is 4. Even though we know that the answer is 3, but what we don't know is if we ran it the next time, it would have given me a 3. I just don't know that. But I ran it a million times, and it's a fair experiment. I'm going to not talk about this. This talks a little bit about what we do in quantum. But I wanted to get to the next stage, and the final slide. I wanted to talk a little bit about neuromorphic computing, because that is another thing that we are looking at also. And the idea here is this is something similar to how brains operate. This is very interesting to NASA because of two reasons. One is neuromorphic computers can be used, and first of all, they are more advanced than quantum computers. Intel has neuromorphic chips, IBM has neuromorphic chips, Google has a tensor processing unit, HP has this thing called the dot product engine. So you can use them as embedded computing. So you can actually put them in drones, you can put them in vehicles. So you can basically do in situ decision making. So you can basically do what is known as edge computing, because you can put these neuromorphic processors on your sensors and do computing there. So that's one advantage of it. The second advantage of this are these are extremely low power, and they're very easily radiation hardened. So I can actually put neuromorphic processors on space vehicles. So I can actually go off and do kind of in situ decision making. So if I have these neuromorphic processors on some submersible explorer on Europa or something, I can make decisions there. So again, that brings me to the end of my presentation. I'd be happy to take any questions, but the idea is that from the kind of work that we do in our directorate, in my directorate at Ames, which is the Exploration Technology Directorate, it's focused on a variety of technologies. Again, I talked about only one of those, which is high performance computing, which is one of my main divisions. My other divisions are focused on autonomy and robotics and data mining and prognostics and diagnostics. My third division is focused on entry systems technologies. That's where the arc jets are, and that's where we look at materials. And my fourth division, which is the most interesting division in some sense, it looks at human systems integration, because we all get wrapped up about technology, but the idea at the end of the day is going to be, if you're still going to have humans and we are going to do human missions, then there is it's important to understand how humans interact with the machines. And we have to be absolutely sure that there are certain things machines do better than everything else, so we should let the machines do that. But there are certain things the humans do better, and so we should let the humans do that part. But how do we make sure that that interaction between humans and machines work? Again, that brings me to the end of my presentation. Happy to take any questions.